Dr. Caitlin Hodges is an assistant professor of critical zone geoscience at the University of Oklahoma. Her lab's research focus is at the interface of soil science and biogeochemistry, encompassing research questions in the soil carbon cycle, mineral weathering feedbacks, and redox cycling in upland soils. Dr. Hodges is particularly fascinated by low oxygen processes in well-drained upland soils and the influence of these conditions on soil carbon and nutrient cycle. The scale of her lab's work spans from mineral interactions at the micron scale to tracking biogeochemically relevant reactions in soils across broad gradients that cross ecosystems. She and her lab use this fundamental research to understand the role soils play in modulating the global carbon cycle and terrestrial inputs to surface waters. Dr. Hodges received her PhD in soil science and biogeochemistry from Pennsylvania State University and her Master's of Science in Ecology from the University of Georgia. Her topic of discussion today is tracking seasonal metal redox cycling in upland soils with in situ measurements. As a reminder, this session will be recorded and posted on the Junior Science YouTube channel. Now, let me pass the mic to Dr. Hodges.
All right, thanks for that intro. I'm going to apologize ahead of time for my dogs. I just moved around a bit this morning, so if you hear some jangling on my screen, oh wait, I'm disabled to share screen. So
I think you have power now, right?
Okay. Great, I have it. Thank you. All right. And let's get this going. All right, thank you so much for the invitation to share some of my research with you all this morning. Like was said earlier in my introduction, I am newly an assistant professor at the University of Oklahoma in the School of Geosciences. And my work focuses a lot on redox processes in upland soils. And today I will be speaking about a lot of my dissertation research that took place at the Susquehanna Shale Hills Critical Zone Observatory. And so before we jump into some of the research, I just want to say thank you to my two co-advisors, Jason Kay and Sue Brantley, and then also Jay Reagan, who was crucial in the development and implementation of some of the electrodes that I'll be speaking about a little bit later today. Additionally, the K lab was awesome in helping me process samples and sample soils. We would, dress up like fruit or whatever and go out and sample, which was really fun. The Shale Hills Critical Zone community helped develop a lot of these ideas and was a great sounding board for kind of thinking through some of these processes. And then of course, NSF funded this work through the Critical Zone Observatory, and then also through the SITS Signals in the Soils program. And then some of my research was also funded through a USDA NEFA predoctoral fellowship. And so a brief overview of how this talk is going to go. I'm going to try to keep it around 30 minutes so that we can have some time for discussion. So first, I'll introduce my research approach and how I approach and think about these redox processes in upland soils, and then jump into two projects in which I was tracking iron redox and manganese redox in soils at the Shale Hills Critical Zone Observatory. Specifically, this paper that was published in 2019 in Soil Science Society of America journal, and then a second one that is in prep for submission to ES&T. And then we'll touch briefly on implications, and then like one slide about some future directions of what I'm thinking about doing and what I'm starting to do at the University of Oklahoma. So throughout my career, I've been fascinated by these low oxygen processes in upland soil. So thinking about how redox reactions that are thought of as being, low oxygen, so they happen when there's not any oxygen around, but in systems that look like this, well drained, and then soils that look like they're well drained with plenty of iron oxides that have been oxidized, right? So it's like the reduction of iron oxides coupled to the oxidation of organic carbon. And so I'm interested in these processes, not just because they're a paradox and like, why are these happening, but also because they exert strong controls on carbon mineralization and nutrient cycling. So if we think about soils and microsites in soils, right, there is this continuum of low oxygen processes where around a soil bed in like a macro porosity, there's oxidation of organic carbon coupled to the reduction of oxygen. And then we go through, we have like, nitrate reduction, manganese reduction, and then we have iron reduction, sulfate reduction, and maybe in the center is methanogenesis, micro pores that are limiting the transport of oxygen within like the soil. And then of course, this exerts can, oh, sorry. But so, and of course, this exerts strong controls on the oxidation rate of organic carbon. So, and then methanogenesis is the least efficient. And so if we have these low oxygen microsites in soils that are uplands, this is following of organic carbon mineralization. And then of course, specifically iron oxides and manganese oxides are in short range order phases of these oxides act as sites of sorption for organic carbon, and then also other metal cations that are essential nutrients to plants and microbes. And so under oxidizing conditions, the iron and manganese oxides retain organic matter and the cations, but then upon reduction, so lower oxygen conditions in soils that then necessitate microbes to use iron as a terminal electron acceptor, then that could be, that reduction could be a mechanism of mobilization of organic matter and cations. Additionally, this is thought to be a key control on phosphorus movement and transport in soils. And so I'm really interested in these processes, and today I'll be talking to you about how I can use oxygen and CO2 concentrations in soils to kind of decode these redox processes. And this is how I did it at the Shale Hills Critical Zone Observatory. So the CO2 and oxygen system in soils, of course, is mostly controlled by roots and heterotrophic microbes, right? So roots and microbes are respiring and they're producing CO2, and then that CO2 diffuses out of the soil system. But of course, then there could be anaerobic respiration where these heterotrophic microbes, rather than doing aerobic respiration, are augmenting the soil CO2 system, and then that CO2 is also diffusing. And then CO2 could not just diffuse, but then could also dissolve into pore waters to become dissolved in organic carbon that then acts as a weak acid that weathers silicate minerals or carbonate minerals, and then that dissolved inorganic carbon could potentially leach to the groundwater. And then if we index all of these CO2 processes to oxygen, where oxygen is diffusing into the soil system, being consumed by roots and heterotrophic microbes, but then also potentially consumed by reduced metals through oxidation reactions, or even through a process like nitrification, then we can use that ratio of oxygen to CO2 to understand the main controls on soil and oxygen, and then potentially decode these oxidation reactions that are involving oxygen, but then of course also the anaerobic respiration involving solely the production of CO2 without consumption of oxygen. And so I use this method at the critical zone, the Shale Hills Critical Zone Observatory, in the Garner Run watershed, which is a sandstone watershed, and the Shale Hills watershed, which is an acidic shale watershed, so right here. And then I also did this in the coal farm watershed. I'm not going to talk about this system because it's totally different from Garner Run and Shale Hills, but if you're interested, the paper just came out in JGRB. And so these two soils are similar in that they're high in iron oxides, and they have these large cobbles in the case of Garner Run, which is the sandstone site, and then channers in the case of Shale Hills. But they're also different in that Shale Hills has more shallow soils. So these soils are about 40 centimeters deep at the mid slope, and then they get to about 100 centimeters deep at the valley floor. And then Garner Run, the soils are deep throughout, where the soils are about 150 centimeters across the whole Hillslope, the whole Katina sequence. And also at Shale Hills, the soils are on the siltier particle size fraction, whereas Garner Run has more coarse particle sizes, so it's like a bit sandier. and that produces more macroporosity. And because these soils are deeper with greater macroporosity, the rooting depth is also deeper at Garner Run. And so I measured soil CO2 and oxygen at the valley floor, the mid-slope, the ridgetop, and then another mid-slope at both Shale Hills and Garner Run. And then I measured these gases at 20 centimeters, 40 centimeters, and then directly above the sea horizon, which of course varied by Hillslope position. Today, I'll only be talking about the valley floor mid-slope of both sites, just to conserve time. And so I'll be presenting my data mostly like this, where we have CO2 on the y-axis, oxygen on the x-axis, and then we have this theoretical slope of negative 0.76, which represents the one-to-one relationship of CO2 production to oxygen consumption, corrected for the differences in diffusion of oxygen and CO2, because oxygen diffuses more quickly in CO2 and gas. And so if the plots below, if the points plot in this lower half, then we think of that as being less CO2 than we anticipate from aerobic respiration and diffusion, or less oxygen than we would anticipate from aerobic respiration and diffusion. And so some processes that could cause the points to plot in this lower half and not on this theoretical slope would be oxidation reactions. So in this case, we're really going to be thinking about oxidation of reduced metals. And then there are some other processes that are not relevant for this talk, but it could be dissolution of CO2 in soil water. And then of course, silicate weathering, carbonate weathering, consuming that dissolved inorganic carbon and weathering reactions. And then if the organic carbon that was being mineralized, the carbon use efficiency changed significantly, so such that lignin and lipids were mostly being mineralized, then it could also shift the points to plot in this lower half. Okay, and so then we have this other half of the plot where we have more CO2 than we would anticipate from aerobic respiration. And really, the only process that we're going to think about is causing this more CO2 that we would anticipate is anaerobic respiration from heterotrophs. So that would be CO2 production without oxygen consumption. And then in other cases, degassing of CO2-rich soil water could cause this, precipitation of carbonates, which releases a CO2 in the gas phase, or organic acid mineralization, again, because of that carbon use efficiency. And so, this is a simplified idea or a simplified system that we're thinking about. And so, of course, there are other processes that could be affecting CO2 and oxygen in the soil gas system. But, suspend all of those other cases. We're just going to think about a very simplified way of interpreting these data that I collected. And so moving into some of the data. So first, we're looking at the Garner Run site, so the sandstone watershed, and we see this dotted red line representing the one-to-one relationship of aerobic respiration corrected for diffusion, and this black line is the regression line, and then the points are all of this individual data points that I took at the different depths, color-coded based on the day or the month that I collected those data. And so we have the valley floor site and the mid-slope site. And what we see at Garner Run, the sandstone site, is that consistently at both the valley floor and the mid-slope, there are points that are plotting above the dotted red line, indicating that there's more CO2 than we would anticipate just if only aerobic respiration was controlling the soil gas system. And so, we can deduce from the simplified model that likely there's a lot of anaerobic respiration that's going on in both the valley floor and the mid-slope soils at Garner Run, especially in the late growing season and in the summer. So June, July, August, September are really when we're seeing those color-coded points plotting above the dotted red line. Okay, so moving on to Shale Hills, we see much different pattern. And so the valley floor and the mid-slope are different at Shale Hills. We don't see the same types of patterns. And really, the regression line that's representing, like the average of all of the processes in the soil gas system for both are not significantly different from the theoretical line representing aerobic respiration and diffusion. And however, at the mid-slope, we see that the diffusion is a lot faster because we have those channers that are kind of facilitating the diffusion out of the soil gases. And then in the valley floor, we see this interesting pattern where during one growing season, in the late growing season of like August and September, we see these points that are plotting above the dotted red line or the dashed red line, which are indicating to me that in this one growing season, we did have anaerobic respiration. And I dug deeper into these data, and this was during a period of high precipitation, a year of high precipitation. And so that supports more that it's likely anaerobic respiration that was going on in the late growing season. Whereas in general, during the late growing season and other years, we really saw aerobic respiration. And then we even saw maybe some points that were below indicating oxidation reactions. And so comparing the two sites, we see that there's vastly different. And so Shale Hills, we see mostly aerobic respiration, maybe some oxidation, maybe some reduction based on the climatic conditions. Whereas at Garner Run, we see consistent anaerobic respiration throughout the growing season, but especially in like the summer and early fall. And so we hypothesized that what's causing this at Garner Run is, again, because the soils are deeper and because the roots are rooting deeper, likely to get to the water that's deeper in the Garner Run sites. When there is a precipitation event, the roots are then sucking up all the oxygen that's down there, but the precipitation is then limiting the diffusion of new oxygen into the deep subsurface, which is then causing the microbial populations that are associated with those roots deep in the subsurface to switch over to using alternate terminal electron acceptors such as iron or manganese in these Garner Run sites. And so if we're looking at these relationships between oxygen and CO2 with the depth over time, and so I've color coded it such that these cooler colors indicate that the points are plotting in this lower half. The warmer colors indicate that the points are plotting in this upper half. And so we're plotting it with depth over time. We see that at Garner Run, the sites are like it's just kind of loosey-goosey. Sometimes we have some anaerobic respiration, sometimes we don't. Whereas at Shale Hills, we see some more strict seasonal controls, whereas, where we have anaerobic respiration in like 2015, and then mostly nothing going on in 2016, maybe some oxidation reactions ongoing throughout this period, and then maybe some anaerobic respiration again in 2017. And then just to try to convince you all of my hypothesis for Garner Run, we have oxygen and CO2 continuously sensed data where oxygen is in blue, CO2 is in green, and then we have precipitation events plotted on this lower half. And so I'd like you to focus on this one arrow that's indicating this high precipitation event. And then immediately following this precipitation event, we see a decrease in oxygen and a jump in CO2, which is what we'd expect because it's stimulating respiration. And so all that oxygen is getting sucked up, and the CO2 is that one-to-one relationship. But then as oxygen concentrations start to recover in the soil system, and so this is at 140 centimeters, we see that instead of having that concurrent decrease in CO2 that would be representative of that one-to-one relationship between oxygen and CO2 that we would expect, instead we see as oxygen is increasing, the CO2 is actually increasing at the same time, which then, because it's like it's a disconnect between the one-to-one consumption and production, we hypothesize that this pattern is due to anaerobic respiration. And so just to sum up how we think about the redox reactions that are going on in Shale Hills and Garner Run, but especially Shale Hills that seems to be more seasonally controlled. We have summer precipitation events. And so if there's high precipitation in the summer, the roots are sucking up the oxygen, these low oxygen microsites in the soils to become reduced. And then that iron 3 and manganese, or that iron 2 and manganese 2, then just hangs around. Then in the spring, when the oxygen and the soil start to dry and the oxygen starts to come down into the microsites, those microsites become and then all that oxygen is consumed through oxidation reactions. Okay, so we have this conceptual model that I've created of the metal redox cycling at Shale Hills, but it's difficult to verify with like in situ direct method used to infer what's going on, but that's not actually giving us rates. That's not giving us, the products of those reactions, wells to measure CO2 and oxygen, but then also things like redox electrodes, like platinum redox electrodes, are a pain in the butt. This was me using redox electrodes in Hawaii, and I shed some tears trying to make the platinum electrodes work for me. And so I sought to find a way to measure directly these redox reactions in situ. And I collaborated with Jay Reagan, who is a professor at Penn State in civil and environmental engineering. And he is an expert in these fixed potential electrodes that are commonly used by electrochemists in laboratories. And we tried to figure out a way to install these in upland soils so that we could measure iron and manganese reduction and oxidation rates in situ. And so this is us testing them out with just a beaker full of some wet soil. And then this panel on the right indicates this is the electrodes, which were just graphite bars that then we connected to a potentiostat that held a redox potential at constant rather than measuring the change in redox potential. So again, we installed these at the valley floor at Shale Hills, where we saw that strong seasonal control of iron redox and perhaps manganese redox. And so this is me sticking my hand down into a hole to install the graphite bars. This is kind of what it looked like, where we had the working electrode, a reference electrode, and a counter electrode. And so we installed these fixed potential electrodes that were fixed at about 100 millivolts, which we anticipate to be the redox potential where iron is most actively being oxidized and reduced, and then also fixed in 2020 at around 400 millivolts, which is what we anticipate as being where manganese is most actively oxidized and reduced. And so we installed these again at Shale Hills in the valley floor, and we also made some concurrent measurements of pore water chemistry, soil moisture. We did a 3D ERT array in 2020, and then we also measured the soil gases. And so just diving into some of the results from 2019 in the spring. So again, we're measuring current rather than like millivolts. And so if the current is positive, that means iron reduction. And then if the current is negative, that indicates iron oxidation. And we installed those platinum or the graphite electrodes at 50 centimeters and 70 centimeters. And what we see are these three distinct redox events in May, about May 8th, May 10th, and May 18th, where we see reduction at 70 centimeters and then a little bit of oxidation at 50 centimeters. And when we line up these potential or these currents that we measured with some of the water table and precipitation data, what we see is that these are strongly linked to fluctuations in the water table, especially, the water table is coming up to the depth of the lowest electrode, 70 centimeters, which is then generating this reduction that we see at 100 millivolts. And then following in fall 2019, there are much drier conditions in this fall. And what we see is no activity at 70 centimeters, likely because the soils are too dry. But then we do see these fluctuating oxidation events at 50 centimeters, which seem to be linked with the precipitation events that are going on from September 15th through November 1st. And so what we hypothesize is that the oxygen charged rainwater is coming down, it's percolating down to that 50 centimeter electrode, and it's like activating oxidation at 100 millivolts. Okay, so moving on to 2020, where we installed, in addition to that 100 millivolt electrode, the 400 millivolt electrode to measure manganese redox. So in spring 2019, we see the water table and precipitation it's pretty, the water table is fluctuating up to and above the lowest electrode, whereas in 2020, it was much drier conditions. We had the water table never got to the depth of that lowest electrode, and we really didn't have very much precipitation over the monitoring period. And so, as we would anticipate from those conditions, we really didn't see any activity at the 50 centimeter electrode, so I'm just gonna ignore it. And so at 70 centimeters, though, we did see some activity. So the iron is again in this brown color, manganese is in this pinky color, and we saw consistent oxidation of iron at 70 centimeters. But then at manganese, we saw some really dynamic activity where we saw a lot of oxidation in the beginning of May, and then we saw these flashy events of reduction of manganese at 70 centimeters where that current becomes positive kind of throughout the spring. And so so just before we move on, these manganese fluctuations somewhat relate to the precipitation events that are going on in June and July and May and June, but also we think that there's something else that's going on that's controlling the manganese oxidation and reduction because they're not tightly linked like the iron was. And so we're still kind of digging into what is going on with the manganese redox at 400 millivolts. But what's interesting is that about half of the organic carbon in the surface and B horizon in this valley floor is associated with short range order metal oxides. And so we see that, so the dashed triangles are the short range order metal oxides, and then the crystalline metal oxides are the black circles. So if we're just focusing on short range order, we see very little iron that's short range order, and it's mostly manganese and aluminum. And so what we see is that these manganese redox fluctuations in the subsurface of Shale Hills are likely tightly controlling the organic carbon cycling at this site. And so we're kind of interested in thinking about what the implications of these oxidation reduction cycles on fast timescales and what the implications of that are for organic carbon cycling in this subsurface environment. And especially when we're thinking about future changes in climate in Pennsylvania and how more or less precipitation will stabilize or destabilize the organic carbon that is in the valley floor of Shale Hills. And so here are some in-lab incubations that I was doing with the soils in the subsurface. And we can see these little manganese oxides that formed after a week of incubation at field capacity. I thought that that was a pretty cool representation of how manganese oxide rich the Shale Hills sites are. And so not only am I interested in this at Shale Hills, but with my research at OU, I'm interested in probing the relevance of these iron and manganese redox processes to organic carbon cycling across sites of the US, and especially in Oklahoma, where we have strong seasonality of precipitation and soil moisture, where instead of having quickly cycling oxidation reduction cycles as what we saw at Shale Hills, we have maybe one really big reduction event and then just a long prolonged oxidation event. And so I'm working with undergraduate researchers to start sampling some soils and do some in situ or some laboratory experiments with roots and growing roots in these soils and looking at manganese and iron oxide controls on organic carbon. So with that, thank you so much for your attention, and I would love to discuss more. Oh, sorry, I see all of these messages about how you guys couldn't hear me. So I'm sorry about that. But I can stop sharing.
That was really fascinating, Caitlin. Yeah, I think a lot of people might have questions like that. I mean, because we didn't hear some important.
Sorry.
Your finished slide about the association of short range order The organic matter is primarily associated with short-range order iron and manganese versus crystalline.
Mhm.
I think you were talking about this, but I wasn't. Something stopped. Do you have knowledge of that connection between maybe pulse DOC production during one of those reduction events and then utilization of that DOC in heterotrophy?
So that is one of the areas of research that I'm really interested in pursuing, is doing some laboratory manipulations to look at, oxidation reduction cycles and whether there's some release of DOC and then, subsequent like flush of organic carbon use by, microbes. So I do not have that yet, but that is definitely an area that I'm interested.
Caitlin, hi, this is Neil Blair.
Hi.
Cool stuff. So your interpretation of your slopes, CO2 and oxygen, are totally dependent on the assumption that you're dealing with molecular diffusion of CO2 and oxygen through air, if I understand. That's the ratio of the diffusion coefficients. And yet when you got to the sandier site, you got almost perfect, I would say an ideal stoichiometry for carbohydrate oxidation with non-molecular diffusion transport. In other words, some sort of advective transport. When I first saw that, I go, that's not anaerobic processes. That's that's advective transport. And then later in your presentation, you start talking about rain bringing stuff in. I'm also wondering about the biological pump in the soil. In other words, the plants actually injecting CO2 into the subsurface, basically defeating the molecular diffusion thing. So have you guys thought through all this to try to eliminate those as possibilities? I have no doubt there's some anaerobic processes going on, but for them to really move your slope, there's got to be something happening to the reduced products so that they don't get reoxidized. And in most systems I'm familiar with, they are mostly reoxidized such that the oxygen is actually a good surrogate for the total, if you know what I mean. And so I'm kind of wondering what makes your system so different that you think you can use that slope in the way that you have.
Sure. So I agree that, so one, we have thought about advective transport of both oxygen and CO2. And one thing that in these sites that is limiting advective transport is the high soil moisture. They're pretty wet. And so even if the roots, of course the roots are pumping CO2 and sucking up oxygen, but the soil moisture is preventing a lot of the quick transfer. Additionally, one of the things that's going on in the subsurface of Garner Run that I didn't really touch on is that there is a fragipan at 140 centimeters that's perching the water table, and at the mid slope there's transport of across the fragipan and then down slope pretty quickly. And so that's one of the things that we're thinking is going on, is that there's this preferential subsurface lateral flow path that is kind of taking stuff away. But I agree. This is a comment that I get a lot, is thinking of, as people are like, well, what about effective transport? So we have thought about it. Yeah.
I have a question. You mentioned roots theorized impact on oxygen consumption and diffusion into soils, as well as that impact on electron acceptors other than oxygen being used. If you were to compare like prairie and agricultural soils, would you anticipate a greater use of alternate electron acceptors in prairie soils where roots penetrate a little bit deeper?
Yeah, well, sure. So in prairie soils, sure. Sorry. Yeah, I think so. That's one of the things that I'm interested in with that box that I showed at the end. The undergraduate student is actually going to grow some prairie grasses to look at the oxygen consumption of prairie grasses over time, We're going to use some planar optode systems to look at both oxygen and CO2 concentrations around the roots. And so my hypothesis is that because the prairie roots are deep, and then also you have like kind of a net sort of system going on, there may be more root associated anaerobic respiration than maybe with the trees. And then agricultural systems, I think that probably a lot of that is dominated by nitrogen because they're being supplied a lot of nitrogen. And so I think that a lot of the anaerobic processes get poised on nitrate reduction because that yields a lot of energy.
Do you think that would be, I mean, obviously the nitrate additions from fertilizer would be very impactful, or I guess more in the shallower areas of the subsurface, but deeper where maybe nitrate doesn't penetrate as deeply and there's maybe a larger, I guess, larger concentrations of iron. You think that iron might dominate it a little bit more then?
Yes, yeah, I think so.
If I could jump in, I think that last comment or exchange is really pertinent. Where we're working, Caitlin, in poorly drained soils in the Midwest where you have tile drains. And so you have these, unanticipated zones of oxygen injection and amorphous iron manganese deposits forming underground where it would normally be anaerobic. And so you have this inverted profile at depth. This double diffusion essentially, and double precipitation. And so this is kind of one of the things I was really kind of hoping with you coming to spark some of this conversation about the metal connections with the organics and the oxygen, but we think about it from both directions.
Yeah, that's really interesting to think about how there's like this zone in the middle, like the B horizon is really the most active like anaerobic zone potentially, but not the deep subsurface.
So if you had to do things different for the work you presented in your thesis, what you've learned now, would you have set the system up any different way? I mean, don't worry about money limitations. What would you have done? Other than putting your own synchrotron or something on site, what would you have done?
Yeah, so I think that some of my work was pulling together data sets that were not originally intended to be used in the way that I used them. And so it was more like coming up with a story. And so I think a lot of what I would want is one, the CO2 and oxygen sensors were starting to malfunction by the time that I arrived at Shale Hills. And so I would have installed oxygen and CO2 sensors at all of my sites, that were working because the oxygen, like the hand sample data are really interesting, but also one of the things is that when the soils are saturated, you can't get the hand sample data, or when the soils are, exactly, when they're saturated because the wells are filled with water. So I think that there's that. I think also I would want to do some more, if we had a better way of sampling soils at Garner Run, because there are those big sandstone cobbles, it's really hard to sample soils. It's really hard to do any work out there. And so we pretty much collected those data and then we decommissioned the site. And so I wish that there was an easier way for me to have done some soil coring out there to better characterize what's going on in that system, because I think it's really interesting, but I think a lot of people lost steam out there and they moved on to soils that at a farm that were a lot easier to sample. I think those are the two things.
I have one more question. I know you mostly focus on well-drained soils, but
Mhm.
in our context of like poorly drained soils, water's inhibited percolation can limit oxygen's diffusion through the through pore space. And do
Mhm.
you think that like pooling of water at shallower depths could substantially impact the redox properties of soils deeper in the subsurface?
Mm. So you're thinking about, so are you talking about like a perched water table where there's perching shallow and then it's not necessarily saturated below that, or?
Yeah, I was thinking we're like in the event of like rainfall.
Mhm.
In well-drained soils, it'll percolate through the, I guess, through the subsurface at a much faster rate. But in poorly drained soils, it can kind of maybe be more saturated in the upper part of the subsurface and not so
Mhm.
much in the lower part. But that can also diffuse, or it can also inhibit oxygen's diffusion into that
Yep.
subsurface. That's kind of where I'm trying to.
Okay. Yeah. So I think that in some ways, the poorly drained soils that you're working in were, and even though we're thinking about like the surface, I think that there would probably be more reduction upon saturating conditions, just because there's more organic carbon there for the microorganisms to use. And so there's not very much organic carbon at 50 and 70 centimeters. And so they're really dependent upon the DOC that's like percolating down. Whereas in your system, there's probably a lot of DOC and organic carbon for the microbes to start using for their respiration, regardless of what terminal electron acceptor they have available for them to use. And then thinking about how slowly things are percolating, and then oxygen is maybe limited in the subsurface, even if it's unsaturated. I think that's interesting because you probably have more oxidized species underneath, especially if it's a tile drained system. But then it's kind of like recharging all of the iron that could then potentially be reduced during anaerobic respiration. And so you have probably less transport of iron away from the system and more just like flashier oxidation reduction cycles closer to the tile drain.
Thank you. All right. Do we have any more questions?
I was going to ask one. Hey, Caitlin. Thanks. Interesting talk. So I'm wondering if you thought about, you show these flashy switches between aerobic and anaerobic. And maybe this is outside the scope of your work, but what does that mean for greenhouse gas fluxes out of these soils? What can we learn from this really detailed study?
Yeah, so that is something that I'm interested in, is coupling the samples that I take at different depths with some flux measurements, because I think that is, I don't know, when we're thinking about like global change and also Earth system models, I think that it's important to link anaerobic respiration and these processes with, gas fluxes that are relevant to our Earth system. But I think, so I did like a back of the envelope calculation for Shale Hills and Garner Run, especially Shale Hills, though, thinking about the anaerobic respiration and kind of like in sum, how much CO2 flux that added to the system. And in the late summer, it was like 25% of the CO2 that was coming out of like the valley floor at Shale Hills was associated with anaerobic respiration, at least in that wet year where we had, if we were thinking about like the lines, right? We had the 1 year that was aerobic respiration, then we had the other one that looked like anaerobic respiration. So that was what my back of the envelope calculation was, just based on thinking about the slopes at different times of the year. So.
Yeah, that's interesting. I should think about this more, because in the atmosphere, we use the CO2 relationship, and there's some assumptions about what the oxidative ratio of photosynthesis and respiration is. And if this hasn't been taken into account, I wonder if that changes the math a little bit.
Yeah.
Okay. Cool. Another thing I was wondering too, so you see the rain events feed oxygen into the subsurface. Have you looked at the temperature sensitivity of that? If we have warmer rain events, does it mean less oxygen pumped into the subsurface?
Yeah, so I have not looked so much at temperature sensitivity, but when the rain events are colder, when the rain's colder, that also enhances dissolution of CO2 into the rainwater. And so that is a signature that other people have seen, where the rainwater is dissolving CO2 rather than oxygen. But I could also see it affecting oxygen. But because CO2 is more soluble than oxygen and water, I would think it would have more of effect on CO2.
It's cool. It's another climate change angle. Maybe
Yeah.
pull that. Yeah.
Mhm.
Great. So if there are no more questions, I would like to thank our speaker, Dr. Hodges, and the rest of our audience for attending this pop-up webinar. I hope to see you all at the next one, and have a great day, everyone.
Thanks a lot, Caitlin.
Yeah, thank you for the invite. I really enjoyed speaking with y'all.
Hey, Andy, can you stay on the call for just a second?
Sure, yeah, thanks.
So I wanted to ask what happened on the